We are going to look at radiation exchange between gray surfaces. Okay. So to start with, let us say that there are n gray surfaces in an enclosure. Okay. If you have n gray surfaces in an enclosure, okay, n gray surfaces. Okay. Now, the question is, how do we characterize or how do we find the net radiation exchange between one surface and all other surfaces? Okay. So that's the question. So suppose we assume that it's a steady state system, okay, which means that the temperature T1, T2, etc. are maintained constant. Okay. It's a steady state system and it's isothermal. Steady state isothermal system. Okay. And the third one is, if we assume that it's a opaque surface, so which simply means that transmittivity is 0. So the only mode of splitting of the incident irradiation is by absorption and reflection. Okay. And if we assume that it's a diffuse radiosity, okay, and we said it's gray surface, so which means that alpha and epsilon are not function of lambda for a certain range. For a certain range of lambda. Okay. All right. So let's zoom in to one surface. Okay. So let's say this is surface I, and the incident irradiation, the rate at which the irradiation is coming or hitting that surface is AI times GI. Okay. So GI is the net incident irradiation, and if the net emission that comes from the surface is AI times JI, where JI is the radiosity which includes both emission and reflection. Note that this is a gray surface, so there will be reflection. There is no reason to assume that reflection is 0. Okay. So now we could also resketch the same schematic in a slightly different way. So supposing if AI GI is the incident irradiation, then there will be some part which is reflected, which is given by AI into reflectivity, which is rho I. Okay. So rho I is the reflectivity of that surface multiplied by GI, right. So remember the definition of reflectivity. Reflectivity is the amount of radiation which is reflected divided by the total incident irradiation, right. So rho I AI into GI will tell you what is the irradiation that is incident is reflected back. Okay. And then what is absorbed is AI alpha I GI. So that's the fraction of radiation which is absorbed by that surface. Okay. And this JI would essentially be sum of the net emission, sum of the emission from the surface plus the reflection, right. So AI JI, so JI will be emission from the surface plus rho I into GI. Okay. So that's the radiation, that is net radiation emitted from that surface. So supposing I want to maintain isothermal conditions, okay. So assumption number 2 is the surfaces are maintained at a certain constant temperature, right. So if I want to maintain at a constant temperature, then there has to be some amount of heat that is either removed from the surface or supplied to the surface depending upon the radiation exchange. Okay. So Qi, which is the net radiation exchange at the surface, okay, so that is given by whatever is emitted, net emission, minus Gi into Ai, right. So this is the net emission. Ji includes reflection, right. So keep in mind that Ji already includes reflection. So the net radiation exchange is Ji minus Gi into Ai. Okay. So Ji is, so this is emission plus whatever is reflected, and Gi is whatever is alpha plus Y into Gi. Okay. So that's already accounted for. So the net radiation exchange is Ji minus Gi into the surface area. Okay. So now we know that Ji is Ei plus rho I into Gi, but we said that the surface is opaque. So rho I can be expressed in terms of the absorptivity. So we know that alpha I plus rho I equal to 1. Right? So this will be Ei plus, so that should be Ei plus 1 minus alpha I into Gi. Okay. So from here we can find out Gi equal to Ji minus Ei divided by 1 minus alpha. Okay. So now if we substitute that into this expression here, so you will find that Qi equal to Ji minus 1 minus alpha I multiplied by Ai. Okay. So all I have done is I have now eliminated Gi from the net radiation exchange. Okay. So now I can express this as, so a little bit of algebra. So Qi will be Ei minus alpha I Ji divided by 1 minus alpha, okay, into Ai. So all I have done is I have just multiplied 1 minus alpha I and cancelled the like terms, and so it is Ei minus alpha I Ji by 1 minus alpha I. We also said it's a grey surface, so which means that alpha I equal to absorptivity is equal to emissivity of that surface in that particular range of wavelength, right. Now if we plug in this, we will see that Qi equal to Ei minus epsilon I Ji 1 minus epsilon I multiplied by Ai, right. So Ei is the net emission, this is does not include the reflection, so it is the net emission from that surface, but that we can express in terms of the properties of the surface, right. So we know that emissivity is an intrinsic property of that surface, that multiplied by the corresponding black body radiation at that temperature will tell you what is the net emission, okay. So we can write this as Ai epsilon I into Ebi minus Ji divided by 1 minus epsilon I, okay. So we can rewrite this as Qi equal to Ebi minus Ji divided by 1 minus epsilon I, okay. What does this form look like? Recall some of the conduction concepts. Net transport, heat transport rate equal to temperature difference divided by resistance. So it has the same form as what you have seen in resistance concepts in conduction, right. So now we can define, so again it is a definition. So in conduction we said that Q is delta T by the resistance offered by that system for conduction, right. Now where delta T, which is the temperature difference, is the driving force for heat transfer. Similarly for radiation, the driving force for supplying heat or removing heat from that object is actually the difference in the black body radiation at that temperature minus the net emission. So, if we define the driving force for radiation exchange, for heat transport due to radiation exchange, so if we define the driving force as EBI minus JI, okay. So, very similar to the way we define driving force in conduction, the temperature difference as a driving force in conduction, one could define a driving force for heat transport due to radiation exchange as EBI minus JI. So, once we do that, now we can easily represent it in terms of the resistance concept. So, if EBI and JI 1 minus epsilon I by AI epsilon I, okay. What does this resistance signify? So, note that in conduction we said the resistance is the resistance offered by the system for heat transport, right, due to conduction. What does this offer here with respect to its capacity to store heat? Right? So, what does this offer? What is this? What resistance does it reflect? Yeah. Look at the quantities here. So maybe I will give you a hint. So in a 1D system in conduction, resistance is L by Ka, right? So it contains conductivity, length scales and conductivity. What does this contain? Emissivity. So what does it reflect? Okay. So you have to understand the difference. This is a cross-sectional area process, right? Whereas this is a surface area process. So this is the resistance that is offered by the properties of the surface for net radiation that is either absorbed by the surface or emitted by the surface. So if Q is positive, then there is going to be net radiation that is emitted by the surface, and if this Q is negative, there is going to be net radiation which is absorbed by the surface. Okay. So this resistance essentially signifies what is the resistance offered by the surface due to its surface properties for radiation exchange from that surface. So you have to understand the distinction between the resistance, concept of resistance in conduction and concept of resistance in radiation. Okay. Okay, so this is exchange between two objects. Now we said there is an enclosure, right? You have n objects which are actually present in the enclosure. So how do we represent that in a network concept? So we are going to see that next. So n surfaces, I should qualify it by saying gray surfaces and enclosure. Okay. So what is the net irradiation received by a surface? We cannot quantify the net radiation exchange from all the n surfaces if we do not know how to find out what is the net incident irradiation that is actually received by a surface. So note that this is n surfaces placed in an enclosure. Okay, so you have n surfaces, etc. up to n. Okay. So what is the incident irradiation that is received by a surface I? Okay, so let's take out one surface. Okay. So the radiation emitted, the net radiation that is emitted by a surface is given by AI times Ji, right? and I goes from 1 to n in an enclosure. So what is the total irradiation that is received by ith surface? That's right, there is a summation that has to come here, because there is some radiation received from 1, some from 2, some from 3, etc. So there has to be a summation. What is that summation? So that will be summation Aj, so Aj Fji into Jj, right? So J going from 1 to n, right? So this is the radiation that is emitted by jth surface and is intercepted by I summed over all j, right? So if I have surface j, so if this is my surface j, then the radiation that comes out of surface j is Aj Jj, and what fraction of that is received by surface I? That multiplied by the corresponding view factor, okay. So like that it is going to receive from all the surfaces which is present in the enclosure. So therefore the net incident irradiation to ith surface will be sum over whatever fraction received from each of the surfaces going from 1 to n, okay. So the question is, how does it include the absorbed part? We don't have to include that, right? Whatever is received by, let's say, surface 3 is essentially what is a fraction of what is actually emitted, net emission from surface 1. We are going to write an energy balance to reflect the amount that is absorbed, okay. All we are saying is what is the net amount of incident irradiation. We haven't imposed the condition of isothermal system yet. We are going to do that, okay. So we only said that what is the net amount of irradiation that is received by any surface. If I know what is the net emission from a surface, that is what is emitted by itself plus whatever is reflected from the incident, if I know that, then there has to be some fraction of that which is received by surface I, and that summed over all the surfaces is going to tell me what is the total irradiation that is actually received by surface I. That's all I am saying here, right. So let me explain again, okay. So supposing you have two surfaces, okay, surface 1 and surface 2, okay. So I call it surface 1 and surface 2, right. So supposing the net emission that comes out of that surface is Ai times Ji, right. So that's the total amount of radiation that is emitted by this surface, correct. Now this includes the emission by itself plus whatever is reflected because of the incident radiation. Now there has to be some part of it which is received by surface 2, okay. So what is received? So this will be, so I call it A1 J1. So that will be A1 J1 into F12, okay. The fraction of emission that comes from surface 1 and received by surface 2 is A1 J1 F12. Now let us say I add one more surface here, I add 3, okay. So now the emission from here will be A3 J3, right. So whatever fraction that is received by surface 2 from 3 is A3 J3 into F32, right. Now I can add one more, let us say fourth one, A4 J4. So that will be A4 J4 into F41, I mean 42, right. So sum over all of this is the total incident radiation to surface 2. That's exactly what that summation is, okay. Any other questions? So we said that Qi net is Ai into Ji minus Gi, right. So that's the net radiation exchange between whatever is incident and whatever is emitted by that surface. Now we know that Ai Gi is given by the summation that we just derived, okay. So that will be Ai into Ji minus sum j equal to 1 to n Aj Fji into Jj, okay. So now we know that sum Fij j equal to 1 is, what's this expression? Sum of all the view factors is 1, right. So that's a conservation property. So if that's equal to 1, so now I can throw in that expression here. So that will be Ai Fij Ji minus this Ai should be inside. Minus Aj Fji into Jj. So therefore, Q net I will be sum Ai Fij into Ji minus sum Aj Fji into Fj. But we know from reciprocity relationship, right? We know that Ai Fij is Aj Fji. So we plug in the reciprocity relationship, you will see that it will be summation Ai Fij Ji minus Jj. This is sum over all j. Okay. So this is the net radiation exchange with by surface I with all other surfaces in the enclosure. Okay. Note that this is also equal to Ebi minus Ji divided by 1 minus epsilon I by Ai epsilon I. Okay. This is what we derived a short while ago. So the net radiation exchange, because of radiation exchange between one object and all the other objects, that balance will give you this expression here, and this expression here is where you actually impose the condition that all the surfaces are maintained at an isothermal condition, right. So when you put in all those expressions, you will see that the radiation exchange between individual surfaces in the enclosure can be related to the properties, surface properties of that surface, and that comes from this expression. So in what we are going to do in the next lecture, we are going to expand the resistance network that we drew for one surface and how to use the resistance concept to find out the radiation exchange with all the surfaces that is present in an enclosure. So we are going to start with that in the next lecture.